Welcome everyone. I'm excited to embark on this cosmic journey through the fascinating world of physics with you. Physics isn't just equations on a chalkboard, it's the language of the universe, unlocking secrets from the smallest atom to the largest galaxy. From Newton's laws of motion to quantum mechanics, we'll traverse the landscape of physics and uncover the elegance woven into existence. Fasten your seatbelts, open your minds, and get ready for an exhilarating ride. Our journey begins with Sir Isaac Newton, who redefined our understanding of the universe. In the 17th century, Newton gifted us with his three laws of motion, principles so fundamental that they underpin much of classical physics. The first law, the law of inertia, states that an object at rest will remain at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by a net force. Picture a game of cosmic billiards. A celestial object will continue its trajectory indefinitely unless something like gravity steps in to alter its path. Newton's second law, F equals ma, tells us that the force acting on an object is equal to its mass times its acceleration. This law helps us understand why a rocket needs immense thrust to overcome Earth's gravity. Finally, the third law, for every action, there is an equal and opposite reaction, explains why when you jump on a trampoline, you are propelled upward. Let's delve into one of the most fundamental principles governing the universe, the law of conservation of energy. This law states that energy cannot be created or destroyed, it can only be transformed from one form to another. Think of it as the universe's strict budget. Energy can be spent, saved, or exchanged, but the total amount always remains constant. Imagine a roller coaster climbing to the top of the highest peak. As it climbs, it gains potential energy, the energy of position. As the coaster plunges down the track, this potential energy is converted into kinetic energy, the energy of motion. Throughout the ride, energy is constantly shifting between forms, but the total energy remains constant. From the smallest atom to the largest galaxy, the law of conservation of energy governs the flow and transformation of energy. Our cosmic journey now takes us to the fascinating realm of thermodynamics, a branch of physics that delves into the intricate ways energy is transferred as heat, and how this transfer influences the order and disorder within various systems. At the heart of thermodynamics lie four fundamental laws that govern the behavior of heat and energy, shaping our understanding of the physical world. The Zeroth law, a fundamental premise, establishes the crucial concept of thermal equilibrium. It states that if two systems are each in thermal equilibrium with a third system, they are in thermal equilibrium with each other, creating a balance. Imagine 3 cups of coffee, 2 at room temperature, and 1 hot, illustrating this principle. If the hot cup cools to room temperature, it achieves thermal equilibrium with the other 2, demonstrating the Zeroth law in action. The first law of thermodynamics, essentially a restatement of the law of conservation of energy, dictates that energy cannot be created or destroyed, only transferred or converted from one form to another. The second law introduces the concept of entropy, a measure of disorder or randomness in a system, which is a key aspect of thermodynamics. It states that the total entropy of a closed system can only increase over time, leading to the inevitable trend towards disorder. Lastly, the third law states that the entropy of a system approaches a constant value as the temperature approaches absolute zero, where molecular motion nearly ceases. Prepare to be electrified as we venture into the realm of electromagnetism, a fundamental force that governs the interactions of electrically charged particles and the behavior of light itself. This force, encompassing both electricity and magnetism, is responsible for everything from the spark of a lightning bolt to the gentle touch of a hand. Our exploration begins with electric charge, a fundamental property of matter. Objects can have a positive, negative, or neutral charge. Like charges repel each other while opposite charges attract. Moving charges create magnetic fields regions of influence that exert forces on other moving charges. In the 19th century, James Clerk Maxwell unified electricity and magnetism with his elegant set of equations, revealing that these seemingly distinct phenomena were in fact two sides of the same coin. Maxwell's equations predicted the existence of electromagnetic waves, ripples of energy that travel at the speed of light. Hold on tight as we dive into one of the most mind-bending concepts in physics: wave-particle duality. This principle, a cornerstone of quantum mechanics, challenges our classical intuitions about the nature of light and matter. For centuries, scientists debated whether light was a wave, like ripples on a pond, or a stream of particles, like tiny bullets. Isaac Newton championed the particle theory, while Christian Huygens argued for the wave nature of light. Experiments seem to support both views, deepening the mystery. In the early 20th century, quantum mechanics emerged, offering a revolutionary perspective. Light, it proposed, acts as both a wave and a particle, a concept known as wave-particle duality. This duality isn't limited to light, it extends to matter as well. Electrons, once thought of as tiny particles orbiting the nucleus of an atom, also exhibit wave-like properties. Fasten your seatbelts as we embark on a journey through the cosmos of Albert Einstein's theory of relativity, a revolutionary framework that reshaped our understanding of space, time, gravity, and the universe itself. This theory has not only changed the way scientists view the universe but has also had profound implications for technology and our daily lives. Einstein's journey began with special relativity, which he proposed in 1905. This groundbreaking theory challenged the conventional wisdom of the time and opened up new avenues of scientific inquiry. This theory, based on two postulates, that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is constant for all observers, led to some startling conclusions. These conclusions have been confirmed by numerous experiments and have stood the test of time. Special relativity revealed that time and space are not absolute but are relative to the observer's motion. This means that two observers moving relative to each other will experience time and space differently. Imagine two observers, one stationary, and the other traveling at a significant fraction of the speed of light. Their perceptions of time and space would be vastly different. Time would actually slow down for the moving observer relative to the stationary one, a phenomenon known as time dilation. This effect has been confirmed by experiments involving high-speed particles and precise atomic clocks. Furthermore, special relativity showed that mass and energy are intimately connected, as elegantly expressed in Einstein's famous equation, E equals sign mc squared. This equation has profound implications for both theoretical physics and practical applications. This equation reveals that mass can be converted into energy and vice versa. This principle is the foundation of nuclear energy and has led to the development of technologies such as nuclear power and medical imaging. In 1915, Einstein presented his general theory of relativity, which extended special relativity to include gravity. This theory has revolutionized our understanding of the cosmos. General relativity describes gravity not as a force, but as a curvature of spacetime caused by the presence of mass and energy. This concept has been confirmed by numerous observations and experiments. General relativity has been instrumental in explaining the bending of starlight around massive objects, the existence of black holes, and the expansion of the universe itself. These discoveries have deepened our understanding of the universe and our place within it. Our final destination takes us to the very frontier of physics, the enigmatic realm of quantum mechanics, a domain that defies our everyday experiences and challenges our understanding of reality. This revolutionary theory, developed in the early 20th century, governs the behavior of matter and energy at the atomic and subatomic levels. It has fundamentally altered our perception of the universe. One of the most startling concepts in quantum mechanics is superposition, which states that a particle can exist in multiple states at once until it is measured. This idea is both fascinating and perplexing. Imagine a coin spinning in the air. It's not heads or tails until it lands. This simple analogy helps us grasp the complex nature of quantum superposition. Similarly, a quantum particle exists in a blurry cloud of possibilities until an observation collapses its wave function into a definite state. This collapse is a fundamental aspect of quantum theory. Another bizarre phenomenon is entanglement, where two or more particles become linked, even when separated by vast distances. This connection is instantaneous and seemingly inexplicable. Imagine two entangled coins. If you flip one and it lands on heads, you instantly know the other is tails, no matter how far apart they are. This phenomenon defies classical logic. This spooky action at a distance has been experimentally verified, challenging our classical notions of locality. It suggests that the universe is far more interconnected than we ever imagined. Quantum mechanics, while challenging our intuitions, has been remarkably successful in explaining the behavior of atoms, the properties of light, and the workings of transistors that form the foundation of modern electronics. Its principles are integral to the technology we rely on every day. As we conclude this 5-hour expedition through the cosmos of physics, we stand in awe of the universe's elegance and grandeur. From the fundamental laws of motion to the mind-bending world of quantum mechanics, we've glimpsed the intricate mechanisms that govern the reality we inhabit. But our journey doesn't end here. The pursuit of knowledge is a never-ending quest, and the cosmos of physics still holds countless mysteries waiting to be unraveled. So, let us venture forth with insatiable curiosity, armed with the tools of reason and observation, to explore the vast